Hey guys, so um, prepare to take off your physics hats for today and put on your math hats. I know it's your favorite thing. Um, Today we are going to finally get back to finish the story of what is a vector or what are properties of vectors. We've been working through forces and then momentum and conservation laws. We talk generally about it. We're coming up on work, and then later on we're going to need torque. And for both work and then torque, when we get to rotations, we need to be a little bit more sophisticated with our knowledge of vectors. So I'm going to try to give you in a couple of little videos here what I need for you to have, and I'm going to try to be honest, I'm going to say it a little bit higher level than we actually need for Physics 1, because you will use it all day, every day at the start of the fall semester. If you're an engineering major, you will use it in statics, you will use it in linear algebra, you will use these properties in Calc 3, you will, thermodynamics, not so much, but then when we come back in Physics 2 with electricity and magnetism, it hits you like a hammer. So these skills are sort of foundational, and even though I really probably won't need for you to know all of these ideas, I want to spell them out, and I want to be honest, so I'm going to say it the right way, I think, or as best I can in this amount of time. And then hopefully we can do a few examples and you can kind of see in practice how it works. So the starting point is going to be a little bit abstract. That's okay. Try to get what you can out of the first little bit here. That's not what you need to actually grind out numbers for problems and things like that. It's just, I want to say it in a way so that, if you do understand it, then that means next year, piece of cake. And if you don't understand it now, just think of it as maybe, hopefully, it's sort of planting seeds for something to come later. We'll see here. I've changed the projector again. I hope it's not too blurry on the screen. Let me make this larger. Maybe I can tell. I will try to write largely or larger. I guess it fixes the glare, but then it's farther away from the blackboard or the whiteboard. Can't have it both ways. All right. Let's go. So in this video, we're going to focus on something called a scalar product, or more conventionally called a dot product. In the next video, I'm going to talk about something called a cross product. They are different. Some of the formulas look similar-ish. So don't blur them together. Try to keep the two separate in your mind. Okay. So a dot product. So the vectors part 2 generally is what this section of the course is called. And here we have scalar product slash dot product. Okay. So to date, we have seen how, if we think about our algebraic manipulations we can perform with vectors, we can add them, and we can multiply them by scalars to stretch them out or compress them. We are going to enlarge our toolbox to incorporate a notion of multiplication for vectors. So you have to kind of think about that. It's not always clear what that would even mean. And we're actually going to eventually have 2 ways to multiply them. And what I'm promising you is that these are the only 2 ways to define a product structure on vectors that makes sense. Even if they look a little weird at the outset, these definitions make sense. There's a larger way to think of this, but larger multiplication structures can be decomposed into these. So if you understand this, you can do what you want. Other random ways, if you just try to combine vectors to get something, you put stuff in and get something out, most of the ways that you go to do that, to make that set of rules, won't work well for physics, because the way that we define dot products and cross products has to make sense regardless of the choice of coordinates. So the types of product structures, I suppose you can come up with other product structures, I suppose, but they're not going to be things that can come up in nature. Maybe that's the better way to say it. The only thing that can come up in nature is a product structure which transforms well and makes sense to people who use different reference frames. So all observers should be able to use the same multiplication structure in the laws of physics. Okay, a scalar product, and I will call this a dot product, because we already have scalar multiplication, and I don't want you to confuse them. These are different, but a scalar product, a dot product, another name for this is also an inner product. And in my own work, maybe I actually kind of like that language, but I won't use that language in this course. I'm just saying it now because in linear algebra, you will use all these. Okay. All right. So a scalar product. So first, the formalities. Okay. A scalar product is going to be or the dot product is going to be a symmetric bilinear mapping from two vectors to a scalar. Blah, 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 blah. What does that mean? What it means is we're going to have something called a dot product, and it's going to be a way to take, ooh, can't write today. Take two vectors and spit out a scalar. So first of all, weird. Two vectors go in and a scalar comes out. When we multiply two scalars, I get another scalar. Multiplied, normal multiplication, you take two numbers, you get the output looks the same as the input, or it's the same flavor. Here, not so. We input two vectors and we spit out a scalar. So already that's a sign that it's a multiplication structure, right? Because it takes two things and spits something out, but it isn't the same game that you're used to. Okay, takes two vectors and it's scalar. And the other property that it has is that it is symmetric. That means if you do A times B or A dot B, that will be the same as B dot A. So I'll write that out. If I have a vector, I haven't yet told you how to actually perform this process, but whatever the recipe is, it is baked in the cake that A dot B equals B dot A. No way around it. That's just always going to be the case for a dot product. Okay. The other property that we have is that if I have three vectors and I do the dot product of A dotted with the sum of B plus C, then the dot product just distributes the way you think it should. Now, you might be saying, well, duh. But remember, I haven't even told you how to actually do this. I'm just saying, whatever this thing is, it has this property. And I will go and tell you, it's not always true that A distributes, or well, you could imagine trying to construct quantities or things or objects or magical, mystical unicorn numbers, which don't have all these properties. So we need to verify this. So anyway, this is going to equal A dot B, whatever that means, plus A dot C. Okay, so the dot product will distribute over addition. Okay, that's, again, these are properties that are going to be baked in the cake as part of the definitional meaning of this. And the final thing here, I've got plenty of room, okay, is that it is true that if I had a vector A, and I took the dot product with another vector, which was some constant, I just call it lambda times B, this would equal lambda, that same constant, that scalar, multiplying the dot product of A dot B. Okay. So, remember what I said. The dot product is a symmetric, bilinear. Okay, well, don't worry about the bi part, but linear is this. It means that, yeah, it works all right under distribution, and scalar multiplication factors out. So if you kind of like an equation of a line, where if you double x, you double the change in the height of the graph. So that's why they say bilinear, and that's why they say linear, and they say bilinear because of the ability to, because it's symmetric, anything you could do on the second piece, you could have done on the first piece. So it's actually linear in both entries. Okay, symmetric bilinear mapping. A mapping just means it eats this and pukes out that. So it eats two vectors and spits out a scalar. Awesome. We will need this basically never, but now you have it, and you'll see pretty much the same thing, and probably presented in much the same way in linear algebra if you take it, statics if you take it, and also calculus 3. Use these same properties in all of them. All right, that being said, let's come up with a formula, something we can really get our hands on. All right, so more explicitly, we have the following definition. The dot product between two vectors, well, let me draw them first before I get into this. Let's imagine that I have a vector, A, and I have another vector, B. Remember, you can slide them around, but I'm going to draw them so that the two tails match, and the angle between them is an angle called theta. It's the relative angle between them. In fact, just so there's no confusion, I'm going to flip this around a little bit. A, B, theta. So theta is the angle between the vectors. It has nothing to do with the x-axis. So in a problem, you might have to adjust and kind of draw a picture and figure out what is the relative vector between, relative angle between the two vectors. Okay. Now, the definition for A dot B, it is defined to be the magnitude of A times the magnitude of B times the cosine of theta. That is the definition. Now, that's the definition based upon your education, right? So that's assuming you've been up through here to this point in physics, you know how to talk about magnitudes of vectors, and you went through high school trig and you learned about theta and cosine of theta and stuff like that. All right, that's a perfectly adequate definition and a way to start this. There is another bizarro world you could imagine. I'm going to give you another formula for this in a minute. And you can imagine a bizarro world where you didn't know about the magnitude of an angle or a vector, and you didn't know about angles, and then this would actually turn into not the definition of the dot product, it would turn into the definition of things like, cosine of theta. So anyway, we'll see that in a minute. All right, so let's do some examples, okay? So let's do some simple examples to kind of get our feet wet. Well, because of the linearity property, there actually are 1, 2, 3, whatever. They're like whatever, 6 really important examples. And then we can use the linearity property to work anything else out. Specifically, if we can figure out how to take the dot product between 2 basis vectors, unit vectors, remember we already know their angles because they're perpendicular, the angle between them is 90 degrees. So if we can work out the dot product between all of the basis vectors, and then express every other vector in terms of the basis vectors, we can figure anything out. Okay, let's see how this goes. I'm just working just formally, just algebraically, using this definition. It's a weird kind of thing, right? It's a little bit of this, a little bit of that, pull it together, psh, you get something, okay? But we're gonna still have our properties when we need them. All right, here we go. So let's try x hat dotted with x hat. Let's just apply the formula. So A will be x hat and B will also be x hat. What's the magnitude of x hat? 1. What's the magnitude of x hat? 1. What's the angle between x hat and itself? 0. Cosine of 0 is 1. Okay. The dot product between x hat and x hat is just 1. Pure number 1, not a vector, scalar 1. Similarly, really the same logic. You learn that y hat dotted with y hat equals 1, and z hat dotted with z hat, if we had a third dimension, is 1. And if you had 26 dimensions, you just keep going, turn the crank. Okay? Awesome. Let me go ahead and simplify this, or just clean this up a little bit. So these are the diagonal elements. They're diagonal because it's kind of the same in both. All right. Now, what about x hat dotted with y hat? Well, magnitude of x hat is 1. Magnitude of y hat is 1. The angle between them is 90 degrees, though. Right? X, y, they're perpendicular. So cosine of 90 degrees is 0. So I end up with 1 times 1 times 0. It's 0. Similarly, y hat dot z hat equals 0. And x hat dot z hat equals 0. Now, you might wonder why I'm not bothering to write down the other combinations, y times x, or z times y, or z times x. Well, I have the symmetry property. The symmetry property ensures that the answer I get is the same. And so I'm not going to bother to write it out. Okay? So we learn that a unit vector dotted with itself has a dot product of 1, and in an orthogonal basis, they don't even have to be normalized really. If the basis vectors are perpendicular, you're going to get cosine of 90, and you get 0. Okay. Okay, so those are a couple simple examples. I'm going to draw a picture, try to give you a better understanding of what this could be, and then we will work out more general dot products. Actually, let's do another example, and then we'll draw a picture. Okay. So let's imagine I have the following vectors then. Let's say I have 2 x hat plus 3 y hat. That's a vector dotted with oh, I don't know, 1 x hat minus 2 y hat. Okay. Now, if you're really good, if you can picture it, you might be able just to look at it and know the angle. And using Pythagorean theorem, you can find the magnitudes. You could just use this. I can't, right? It's really tricky to kind of see this. You know, if it's kind of steep and in the fourth quadrant, and then this one is kind of steep in the first quadrant, and I can't see what angle that is. So instead, we're going to use the algebraic properties, the linearity properties, to kind of, or really the distributive properties, to pull this apart and write it so that you actually only have to take the dot product between unit vectors, and it's really not so bad. So we're just going to distribute this out, and I'll write it out here since it's the first time, and we're not meeting in person. So normally in person, I'd have you guys kind of work through with your neighbor, but alas, this is what we have. So I'm going to distribute this across the sum. So this is going to give me 1 times 2x hat plus 3y hat dotted with x hat minus 2 times 2x hat plus 3y hat dotted with y hat. Okay, so I just distributed this across. Well, so because it's commutative, because I can do it in either order, just like I can distribute to the right, I can distribute back to the left. So I'm going to distribute back here, and I'm going to get 1, well, the multiplying by 1 doesn't do anything. So I end up with 2x hat dotted with x hat plus 3y hat dotted with x hat. Distribute that. Oh, there should be a dot product there. You've got to be really careful to put the dots there, because it basically makes no sense to just say x hat, y hat. You have to say x hat dot y hat, or later on we're going to x hat cross y hat. If you just say put the two vectors next to each other, gibberish. There's no meaning to it. All right, so I have y hat dot x hat, and I have to multiply by -4. And then I have -2 times 3, it's -6, y hat dot y hat. Dot, not plus, sorry. And if you're thinking, good God, who thought this was a good idea? I don't know. No, I don't know who actually invented the notation, who got started with it, but it's not as bad as it looks. Because, what do you see? This is just a 1. And notice all of these off-diagonal pieces, they're just 0. Because the unit vectors are perpendicular. The dot product between perpendicular vectors is 0. I should have said that. That's really important. The dot product for perpendicular vectors. Okay? Sorry, I should have said that. And then this is just going to give me a 1. So in fact, I get 2 times 1 minus 6 times 1 equals -4. Not so bad. It's a scalar. It's a pure number. It's a scalar. Whew. That looks really gross. Really, really gross. It's actually not so bad. Here's the thing. You're going to, yeah. You multiply all this stuff. Blah, blah, blah. But what actually survives? Don't get lost in stuff, because truly, for most of it goes to 0, or at least half. The stuff that survives is only the pairing between x hat and x hat stuff and y hat and y hat stuff. And the rule is you multiply them, 2 times 1, and then you multiply the y stuff, 3 times 2, negative 6, and then you just add the bits together. That's going to be the final rule that you get. So in fact, with a little practice, you can just write the answer down, piece of cake. Okay, let's do another example and you can maybe get a sense for how easy this is. With a little practice, you never have to write them all out. So let's do minus 4 x hat plus 3 y hat. I don't know. Let's do something on 1. Let's do 2 x hat plus 7 y hat. Now, rather than writing it all down, it's faster if we just kind of pair things up. We know you only get something not 0 when you pair up x with x or y with y. If everything else gives 0, don't even look at it. It's like it's not there. So you're going to multiply it all out, blah, blah, blah. But really, I want to strip out the coefficients of x hat, minus 4 and 2, and multiply them. So if I work out minus 4 times 2, and then I add to that the coefficients of y hat. That's going to be 3 times 7. That's negative 8 plus 21. That's going to be 13. Okay, so that's how that goes more generally. I don't know. I'm not very happy with this glare. I guess we'll push through. Okay. Let's write out the answer then for an arbitrary vector, and then you'll see the pattern. Okay. So for an arbitrary vector, that's no better. You just can't win. For an arbitrary vector, let's imagine I have a vector A, which has the following representation. It has an x component, ax times x hat, plus ay times y hat, plus az times z hat. And let's suppose I have another vector, b, which equals bx times x hat, plus by times y hat, plus bz times z hat. And I just want to remind you guys, this is the vector. X hat, y hat, and z hat are the basis vectors. And the coefficients, the scalar numbers that multiply the basis vectors, are called the components. So this is the x component of A, the y component of A, and the z component of A. And if we were to take the dot product between A with B, now these are all symbols, okay? But the power of this is that if we can figure it out for symbols, then we can apply it to any vector, right? These numbers could be arbitrary. So, oh, holy crap, would you have to write all this down? No. The only thing that ever matters is the x component times the x component, multiply them, plus the y component times the b component, y components, plus the product of the z components. So explicitly we would have ax bx plus ay by plus az bz. Okay? This is our formula for the dot product between any arbitrary two vectors. You strip out the x components, multiply them. Strip out the y components, multiply them. Strip out the z components, multiply them, add what you get. And that's how we calculate it. This formula is very useful for arbitrary vectors that go in, if you take statics or dynamics, you get vectors which go every which way, and it's really kind of a mess to even picture it. You just work them out algebraically, Just be careful, you keep this stuff, you write it down, you get what you get. When you just have small vectors, personally, if you can picture it, it's probably easier to use the original formula that we started with. Now, coming back to the bizarro world. In the bizarro world where you don't know about magnitude, and you don't know about about theta, the angles, and you don't know about cosine of theta, in fact, you can use this as a starting point for the definition of cosine of theta. Okay, so that's kind of a, you can imagine some sort of other bizarro world, maybe on Mars when they learn about trigonometry, they actually learn about vectors first and then work backwards to get to cosine of theta. I don't know, never been there. Have to ask them. Okay. Great. Let's, so what I want to do is I want to rewrite this, or use this definition here to come up with a formula for the magnitude of a vector. And then after we do that, then I want to come up with a graphical interpretation for what this whole thing means. It's just like random letters pulled together, multiplied, added, you know, with a double backflip. Well, it's not as random as it looks. I'm going to go ahead and write that. A dot B equals AX BX plus AY BY plus AZ BZ. Those are completely equivalent definitions. Or one of them, you take one of them via definition, you can derive the other. Okay, notice this is kind of familiar. We've seen this sort of structure before. Haven't you seen this before? How do you define the length of something? Okay, maybe the z part you haven't thought about before. But how do you find the z component, or the z, not z, the length of a vector, or the length of something? Well, use the Pythagorean theorem. And what do you do there? You multiply the x component times itself. Okay, so you get 2 bits of x, and then you get 2 bits of y, and you add the results. That's right. In fact, if you take the dot product of any vector with itself, well, from this side, z, that simply equals ax squared plus ay squared plus az squared. Any vector dotted with itself would be ax squared plus ay squared plus az squared. Or using the other definition, what would be the angle between a vector and itself? 0. Cosine of 0 is 1. So a dot a equals magnitude of a. In fact, the dot product between two vectors is the magnitude of the vector, that vector squared. Okay, that's interesting, or it's convenient. It means that, again, in that bizarro world where you didn't know about all the stuff you know, you could start with this definition. You could define the magnitude of a vector simply as its self dot product. And then once you knew how to define the magnitude of itself, you could actually then define the cosine of the angle between any two vectors. You would as a dot b divided by the magnitude of A and the magnitude of B. So if you knew about vectors, and if you knew about vector components, and you knew about this definition of dot product, you could use this to calculate the magnitude of the vector squared. So remember, you have to take the square root to get back to the magnitude. Don't forget the 2 there. And then once you had that, you could pull it all together to find the definition of cosine of theta or the definition of angles. And that's a perfectly valid way to proceed. It's just not how we typically learn. Okay. This is kind of a nice thing. I'm going to erase this. And I want to also point out that if you start with a vector A, remember how we always say that A has a magnitude and a direction. One of the convenient ways then to define or to really kind of spell that out is you can always take a vector and you can write that, you can turn that into a unit vector, A hat. This is a unit vector which points parallel to A, and it simply equals the original vector divided by its magnitude, or using dot products now, we can write this as 1 over the square root of the dot product of A with itself times the vector A. All right, so let's kind of, I'm going to add to my list here. I'm going to say that the magnitude of a vector is the square root of the dot product with itself. And I'm going to define the cosine of an angle between two vectors as A dot B divided by the magnitude of A and the magnitude of B. Just a comment on notation. In many places, rather than writing the magnitude bars with an arrow, they will actually drop the bars and drop the vector when they want the magnitude. I don't want to do that because people, in Physics 1, people tend to get confused between components of vectors and magnitudes of vectors. So I will try to keep everything explicit. Let's do an example using these formulas. Let's do something simple where we know the answer. Let's imagine that I have two vectors. I'm going to say I have a vector A. Let's just take A to be 2 x hat. Really simple. And let's define B to be x hat plus y hat. So if you're picturing these, we have, so A, vector A, would have length 2 and would point along the x direction. So A would look like this. Whereas B would have, well, it would be over 1, up 1. So B would look like this. Okay, so B clearly lies along a 45-degree line. A is parallel to the x-axis. Let's work through these ideas. So, I guess the first thing I want to do is apply this formula for A dot B. Let's use the first formula because I can see the angle. It's not too hard. And then let's also use this formula for it. And, well, we can check that A dot, we can check that this works, and we can check, when we do this, we can check that we get 45 degrees, because we know that. So let's just go through and apply these to A and B. Let's work it out. All right, A dot B. Well, first off, just from the trigonometry, I know that the magnitude of A is sorry, trigonometry, that's just kindergarten. It's 2. And the magnitude of B, well, look at it, it's a 45, 90 triangle. and the base is 1, so the hypotenuse would be the magnitude. That's the square root of 2. Or 1.4, blah, blah, blah. Okay? Great. That's what we get for this, for the magnitudes. So now we can immediately write down the magnitude, or dot B, and that equals the magnitude of A, which is 2, and the magnitude of B is square root of 2, and then we have cosine of theta. All right, and I know it's 45, but let's see that come out here in a minute. All right. On the other hand, we have this formula for the dot product. So we also have A dot B equals, multiply the x components, that's 2, plus multiply the y components. That's known as 0, and we're done. So if I have two formulas for the same thing, I can turn it around and come up with an equation for cosine of theta. So cosine of the angle, I don't know, whatever it is, let's pretend I don't know this 45 degrees, equals the dot product between them divided by the magnitude of A, which is 2, divided by the magnitude of B, which was square root of 2, equals 1 over the square root of 2. Ta-da! That's the cosine of 45. So the angle is 45 degrees, just as we have asked for it to be. Okay? So the formulas look a little complicated. You won't need tons of it in this class. Main things that you will need are this formula, to be quite honest, and to know that perpendicular vectors, when you take their dot products, you get 0. The one thing I did not do yet was turn these into unit vectors. So let's see how that works. Can't remember if we did this in class way back at the start or not. So let's do it this way. A unit vector, which is parallel to A, is simply A divided by its magnitude. Okay. Well, that's pretty trivial. That's going to be 2x divided by 2 is just going to be x hat. Similarly, for B, a unit vector parallel to B would be the original vector B divided by its magnitude, and that's simply going to be x plus y, all divided by the square root of 2. Okay. You can check that these have length 1. Well, this one obviously has length 1 because it's just x hat. Let's check that this has length 1. Let's take the dot product between b hat with itself, because that should equal the magnitude of b hat squared. That's simply going to be the coefficient of x hat times itself plus the coefficient of y hat times itself equals 1. In fact, as advertised, these are unit vectors. Okay, so that's kind of a lightning course of what is a dot product from an algebraic point of view. Let's describe these things from a vector, from a graphical and interpretive sort of way. What does this all mean? So let's imagine I have a coordinate system, and let's imagine, you know what, I'm going to make it really simple here. Well, okay. Let's imagine I have two vectors first, A, and I have another vector, B. Well, let's assume B is a unit vector. What does that mean? So let's imagine B has length 1, and A is some unknown quantity. And then I have my formula. Let's go back to this formula. I'm assuming that B is a unit vector. So if I look at A dot B hat, I work that out. That's A times the cosine of theta, or sorry, the magnitude of A times the cosine of theta. So if you think about that, remember theta is the angle between the two vectors. It's this angle. So if you think about that, the magnitude of A times the cosine of theta, what that actually is you can imagine there's a triangle and A lives on the hypotenuse and B lives along the base, and the dot product of A with B measures the shadow, the length of the shadow of A in the direction of B. What a dot product does, is it reaches in and it kind of measures how much one vector casts a shadow in the direction of another vector. So sometimes we call that a projection. So this dot product with a unit vector is called a projection. So if you'd say the dot product would give you the projection of A in the direction of B, is the way you would say that. So dot products measure shadows in a direction. Okay, and for physics 1, mostly we don't care about that. I mean, it's good to have a sort of a rough mental picture of what's happening, but it's not so important for us unless it's rather than doing arbitrary vectors. Let's rewrite this for x hat and y hat, our special coordinate unit vectors, the unit vectors that we use all the time to describe things. And what I want you to do is to start, or to imagine you have a coordinate system, x and y, and you have some arbitrary vector, let's just call it A, and let's imagine we have, oh, I should have been a little bit more careful, shouldn't I? All right. Okay. So here's A, and here I'm going to go ahead and draw in x hat. It's just a unit vector. And I'll go ahead and draw in y hat, like that. Look what happens. The dot product between A and x hat. Remember, the dot product is supposed to be the shadow of a vector. Sorry, the dot product with a unit vector gives a shadow of one vector in the direction of the other. So if you're thinking about that, what is the shadow of A in the direction x? Well, for this explicit one, it's 3. But it's the x component. So what we've been calling x component, y component, those are just things you can obtain with dot products. And again, in a more formal way of doing all of this, that's what you would define. You would define the components in terms of dot products. You wouldn't start with the components and then learn about dot products. You would go the other way. Okay. So we learned here that AX, the X component, is nothing other than the dot product of A with X hat. Similarly, A dot Y measures the projection of A in the direction of Y. We learned that the Y component is A dot Y hat. Okay, so you can use dot products with unit vectors to pick out components of vectors. Okay. Very good. That's kind of formal. I apologize. There will just be oodles and oodles and oodles of opportunities coming up over the next, over your academic careers to practice these skills. Just trying to get the ball rolling. I guess you have the advantage of having a video. You can kind of go over it and over and over. The book describes all this too. So if you're confused by this, it's more mathematical. I'm really not happy having to do this via a camera and like this. You can look in the book. There are tons of examples on Wikipedia would describe it all. I think though, Wikipedia would be a little more formal. It might be more than you need. There's going to be a sapling assignment practicing these skills. So, all right, I'll let you go there for dot products.